In this video, I presented a solution to an International Mathematical Olympiad problem, but I had to evaluate two pretty terrifying looking expressions. This was one of them. Now, in the video, I passed off the technique of evaluating these as well known, but I think you guys deserve a proper explanation. So, in this video, we're going to evaluate one of them with proof. And I'll make a separate video for the other expression. So the context is this. We have the complex number omega equal to e to the I 2 pi over p. So this I is the imaginary unit. And p is an odd prime number. Now, you want to evaluate this expression in terms of p. Looks pretty terrifying, right? I mean, we have a sum of a product. Definitely does not look friendly at all. But we can kick things off with making this look less terrifying. Maybe expand the product. So this is equal to the sum as j goes from 0 up to p minus 1. And then writing this in expanded form, we have 1 plus omega to the j plus 1, 1 plus omega to the j plus 2, times all the way to 1 plus omega to the j plus 2p. That is what this product looks like in expanded form. Now, we have a sum of a ridiculously complicated looking expression. And what's worse is that we have j's over here. And this j is not fixed. It ranges from 0 to p minus 1. So we might think that this expression is not constant across those values of j. But is that true? Or if it really is not constant, then what can we do? Well, consider this. Notice that we have omega to be a pth root of unity, which means that if you raise omega to the power of p, you get 1. Now, observe this. If you take the same omega and raise it to some positive integer power, such as n, and then you were to maybe write n as mp plus r, where this m is the quotient when you divide n by p, and this r is the remainder. If you write n in this form, then notice what we can do with this. We can write this as omega to the p to the m, and then times omega to the r. And because omega to the p is 1, then this expression just becomes omega to the r. Now, notice what this is telling us. This means that if you take omega and raise it to the n, then this is equal to omega raising it to the n mod p. This n mod p is basically the remainder when n is divided by p. And we've shown that's true, but this is actually going to be super useful for us. Now, check this out. Notice that within this first factor, this very first factor, we have an omega to the j plus 1. So I'm going to extrapolate that. So we have omega to the j plus 1. And likewise, we have omega to the j plus 2. So that's omega to the j plus 2. And this goes on all the way to omega to the j plus 2p, which will be our last one. Now, I want you to consider the exponents on top. Notice that the exponents form a sequence of 2p consecutive integers. Now, why is that relevant? Well, I want you to consider taking the mod p of each of these exponents. What will you get? In other words, take the remainders when each of these exponents are divided by p. What will you get? Well, I will tell you that you will get the sequence 0, 1, 2, all the way to p minus 1, and then this will repeat. So 0, 1, 2, p minus 1. Now, why is this? Well, consider that this is a sequence of 2p consecutive integers. So if you take the remainders when each of them are divided by p, then each modular residue, mod p, will appear exactly twice. So therefore, you get this sequence. Now, it might not be in this exact order, so maybe this j plus 1 might not be 0 mod p instantly, but it's going to be this sequence in some order. Now, what does this mean for us? Well, remember, because of this property, we can rewrite this entire expression as the sum as j goes from 0 up to p minus 1. And as a reminder, again, we're using this identity. This product will become 1 plus omega to the 0 times 1 plus omega to the 1 times 1 plus omega to the 2, and so on and so forth, all the way to 1 plus omega to the p minus 1. But remember, this sequence appears twice, so we actually have to square this entire product. Now, this looks a lot more inviting because we now know that across j from 0 to p minus 1, this expression is fixed, whereas before, having this j over here did not make it look fixed. So it's definitely more convenient to work with this expression. Now, all we have to do is evaluate this product and then square it. But how do we do that? Well, there's actually a very well-known technique for this. I want you to observe the polynomial z to the p minus 1. Now, notice that the roots of this polynomial are the pth roots of unity. So we can write it in factored form. So this will be equal to z minus 1 times z minus omega times z minus omega squared times all the way to z minus omega to the p minus 1. Now, notice that this factored form looks a lot like what we're trying to evaluate over here. But the problem is we have minus omegas, whereas over here we have plus omegas. Thankfully, we can just factor out a negative sign from each of these factors. And because there are p factors in total, and p is odd, then when you factor out all those negative ones, it will still be negative 1, right? So this will be equal to negative of negative z plus 1, and then negative z plus omega, negative z plus omega squared, times all the way to negative z plus omega to the p minus 1. And notice that all the while, this expression is equal to z to the p minus 1. So this is equal to z to the p minus 1. Now, I'm sure you can see where we are going with this. Notice that if you were to plug in z to be negative 1, then this side becomes the product we're trying to evaluate over here. Sure, we have a negative sign, but that's easy to deal with. And we can evaluate it with this expression on the left-hand side. So let's do that. I'm going to have to use this space over here. So plug in z to be negative 1. This product becomes negative of 1 plus 1 times 1 plus omega to the 1, 1 plus omega squared times all the way to 1 plus omega to the p minus 1. And notice that we can use this expression to evaluate when z is negative 1. So this is equal to, that is negative 1 minus 1, negative 2. And there we have it. We just have to multiply both sides by negative 1 to get rid of that negative sign. And there we have it. This product is basically, this product is equal to 2. So this summation, so this becomes a sum as, oh, I'm so sorry, what is that? Becomes a sum as j goes from 0 up to p minus 1 of 2 squared. Of course, 2 squared is just, it's 4. And then we have a sum from 0 to p minus 1. This is the same as 4 added p times. It's equal to 4p. That is our answer. So simple, right? This entire expression is just equal to 4p. As you can see, the techniques of considering the exponents mod p and then using this polynomial, it's a pretty clever idea. It's a pretty clever group of ideas to evaluate this pretty complicated looking expression. Now, if you've been dealing with complex numbers for a reasonable amount of time in math competitions, these techniques hopefully should not feel very strange or alien to you. But of course, I still do admit this is a very beautiful solution. So, that's going to be the end of this video. I hope you found it interesting. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.